So you don't need to digest all the information. I don't expect you to absorb all this stuff in 10 seconds. I've got all the reference material, in particular bibliography. Now, this needs updating, but it has some of the historic papers important if you want to follow up your interest in this field. Just a summary of papers I think you should read, and in particular, the important data analysis papers from Tom White, and also some more recent work by other groups. Caption Brilliance, example, and the first. So the first question people ask is, why would I use an X-ray laser photography instead of a synchrotron? And here's my short list of analysis. With very short pulses, you probably know we can hope to outrun radiation damage. So if you have radiation sensitive crystals, that's the reason that your proposal to use the LCLS might be supported. Remember, the rejection rate's about 80%. You have to be trying to do something that cannot be done in a synchrotron, have any chance of getting a beam type proposal through. Typically, you need to try 2 or 3 times. And radiation damage is one strong argument. We have found, in some cases, with GPCRs, you actually get better resolution with the X-ray laser than with the synchrotron. But we're still early days on that. We don't know the general count. Of course, we can work at room temperature because we're using fast pulses instead of freezing to avoid damage. That's probably the most important sentence from my talk to you. We use the fast pulses instead of freezing to avoid damage. And this allows us to study room temperature dynamics, that's direction research. Of course, we get better time resolution from the picosecond to the 100 picosecond time window. You might want to write that down. Synchrotrons are good for a time longer than 100 picoseconds. In principle, 10 femtosecond pulses, one should expect femtosecond time with a synchrotron. That's very difficult. It's safe to say 1 picosecond, 1 to 100 picoseconds. If you're interested in time resolve, diffraction. And there are papers on that. Geography, so let's follow that up. The point's often made that we can study irreversible reactions. You see, each pulse destroys the sample. So we need a constant supply of fresh, identical samples. But by destroying the process, the sample, we can study irreversible processes rather than the normal sort of stroboscopic method, where you take molecules in a crystal and keep driving them around the same cycle, and as in a discotheque, taking a snapshot at the same point in the cycle each time around, and then adding them together, and then changing the delay, and in that way making a movement. So most of the physiological processes in our bodies are irreversible, and this is a very exciting development because we can study them as long as you can make lots of copies of the molecular system you want to study. You have to keep shooting them in, spraying them across the beam, and they're destroyed by the beam. There are cases where it's hard to grow big crystals, but you can get small ones. And with the liquid or LCD injection schemes I've shown, you can study very small nanocrystals. But you know, this is still somewhat controversial. What has emerged more clearly, I think, is that particularly in GPCRs, there are cases where you can make nanocrystals quickly, but it may take us a year to figure out how to make big crystals. So it's not that you can't make big crystals, it's that it takes a lot of time to do so. And you may know that Nobel Prize Wilker, for example, was in large measure due to his group's willingness to moonlight on other grants for 20 years to figure out how to make the crystal. They spent 10 years learning how to grow a crystal in the transcription apparatus that they're interested in. But the crystals didn't give very good resolution, so they spent another 10 years making good crystals. To go from bad crystals to good crystals for 10 years. So, you know, this is crystallography, the bottleneck in structural biology. That issue is to some extent addressed by the fact that you get showers of nanocrystals from some systems immediately, and they're immediately used for the LCD. Okay, there's this issue about time resolve work where the optical pump laser absorption length is now as big as the crystal for nanocrystals, whereas if you're doing pump work on big crystals, the light doesn't go into the crystal as far as the penetration of X-ray. And you'd like them to be the same. The area illuminated by the exciting light, same as the area or volume investigated by X-ray. Then there's this diffusion time issue. Similarly, in time resolved work where you're looking, say, at catalyst substrate, you want to diffuse some molecules into a nanocrystal. Well, they'll diffuse very quickly into a very small nanocrystal, not a big one. And that time for diffusion sets the time resolution of the technique. So if you have little crystals, you're better off because you get better time resolution. I think I'm just about done. And I've said that you get higher resolution in some cases. Anyway, you can have copies of these. Now, very quickly, how does the X-ray laser work? Copies of which they're out on that kind, right? But here, you see medical X-ray tubes coming up to about 1980, then synchrotrons took over. The thing to remember is that from synchrotron X-ray laser is 10 orders of magnitude more intensity. 10 orders of magnitude more intensity. So if we focus that X-ray laser beam down, it drills a hole immediately in stainless steel. No surprise that it blows up our sample. Now, the 10 orders, you must remember this, is only for the peak of the pulse. It's not the average. And that peak comes along 120 times a second. So if you take the intensity of the peak, it's 10 orders of magnitude greater than the synchrotron at its peak. How does it work? Well, no time for that except just to say that it depends on a thing called a resonant undulator. It turns out that if you bunch electrons with a period between them equal to the wavelength of the X-rays you want, in the relativistic direction, you can get a resonance condition called the self-amplifying spontaneous emission mode, where the gain increases exponentially with distance. So it's an amplifier. Remember, laser, L-A-S-E-R, stands for light amplifier. It does not stand for light oscillator. That would be a loser. And this is certainly an amplifier, a laser. However, it's interesting that John Mavy's paper, who invented this thing at Stanford in 72, he gave a completely quantum mechanical analysis of this problem where he was inventing a Stacey mode. And at the end of the paper, his student noticed that the answer, which they published, did not contain the quantity h bar. And so it dawned on this bright student that this Stacey mode was not quantum mechanical at all, it was classical. He then wrote another paper, which has become the Bible paper of people who want to make these things, showing that you could explain this entirely in the description term of classical electromagnetic. And that's why it has the word spontaneously. You may remember Einstein's 1905 work showing that lasers are based on induced or stimulated emission. That's a quantum mechanical effect. The Stacey mode is not quantum mechanical, so it's self-amplified spontaneous, I mean classical emission. Okay, here it is working, and I'm not sure we can show all of it, but we send flashes of light onto a photocathode. The photoelectric effect spits out electrons. They are then accelerated along a tunnel, a couple of miles long. This is a repurposed particle accelerator. People at Stanford had this thing, particle physics all went to CERN in Europe. So what can we do with this old-fashioned particle accelerator? Now, so we make it into an X-ray laser. That process started in 2003. When Henry Chapman, Dennis Boyd, and I went to a meeting to decide what it would be useful for, because they're going to spend $600 million of American taxpayers' money, and it better be useful. And we made a pitch for biology, and it seems to work. So here, that was the electrons being wiggled to make X-rays, and here they're being separated into two parts. You use a magnet to bend away the electrons, but not the X-rays. And the X-rays then go down into a box. And they then hit these are the electric pulses. They then hit the particles which are being injected here. Read out the diffraction patterns, 120 times a second. So remember this, the shortest pulses can be 10 femtoseconds. Often we work with 70 femtosecond pulses, and you get 120 diffraction patterns read out every second. Then the challenge is to merge them. Now, today's workshop considers these to be little crystals, so these are the Bragg spots, and the method you're learning about is the case where the Bragg spots from different crystals are all just added together. That is, those spots are the same, they're like indices. So if you can index the patterns, all you've got to do is add the 222 reflection from this first crystal to the 222 reflection from the next crystal. When you do that, it's called the Monte Carlo method. And that's what everyone has used up until quite recently. And the research in this field is all about improving on that, going beyond Monte Carlo. So how do you deliver the crystals? Here's our gadget. We make a stream of liquid called a time resolved work. And that breaks up into droplets. You can imagine putting a virus in each droplet. It's a bit like an inkjet printer. And my group at ASU and others, our job is to help you do that. So we can help you with sound delivery. The liquid stream is focused down by a gas jet. We've advised ours the master of all this. And here's the X-ray beam. You can excite the molecule with light if you want to do tons of experiments. Here's a movie of another delivery system called the cubic phase, also developed in Japan. It's a grease gun, or a toothpaste jet. Here, this gooey stuff coming out here. It's like car grease. The cubic phase happens to be a growth medium for nanocrystals of membrane proteins, so which are the hardest, famous, and difficult to crystallize. So this was a wonderful advance because we have in the same little cubic phase a medium in which to grow the crystals and to deliver them. Now, this is the X-ray beam, and it's just drilling a hole. This black line is a hole drilled across a tube, and it's drilling them 120 times a second. This X-ray beam will then go down here to make drag spots on an X-ray detector, 120 times a second, and they're read out as fast as they come in. Now, what are these gaps here? Well, that's very interesting. You see the gap there and the gap there. We found out later that in the control room, they've been sending the beam off to some other team doing a completely different experiment every few milliseconds. That's a spectroscopy experiment. But this is the way you can share the beam. Remember that the LCS is X-ray lasers are serial devices. The synchrotron is a circular device which feeds many stations. That's not the case, and that's a big problem. So that's why it's so difficult to get done. So at any moment in time on planet Earth, only 2 people can be doing an XFEL experiment. One of them is in Japan, Osaka, and the other is in Stanford. That's the problem. Now, there are ways to get around this. Clever people in Hamburg have had the idea of a pass-through where you send the center of the beam, which most of the X-ray beam, of course, goes straight through your crystal for anything, and you pass through a hole in the detector to another experiment. It's serious, so you can imagine, but there are problems with that. It isn't as simple. It's implementation. A big success story has been the use of these LCT jets at synchrotron. And here, these drag spots down here are coming from little crystals which have been injected by that grease gun at ESRA, synchrotron, not an X-ray laser. And the timing, the LCT is so viscous and gooey that the shutter on the detector can be made brief enough so that the crystals don't rotate in the viscous goo while the shutter is open. So instead of using a goniometer, if your crystals are in this highly viscous medium, you could read out more or less continuously. Then, of course, it's not a goniometer, because you don't know what the angles are, what the setting is of the goniometer. But you get the patterns, and you can index them with Tom's clever software later. And this has been called the Rossman's American method, because he first put into all this in fancy papers a long time ago, which is called the American method. That means shoot first, ask questions later. So you just collect the spots and then figure out the orientation, instead of, as Bragg would have done, carefully set up the goniometer for a precise orientation. And write that down in your log. Here's a comparison of different delivery methods. You can read about it later. If all works, you get the fact like this. This is the Brom's group. It's 3-angstrom photosystem 1 or 2, 1. And if you're even luckier and get a whole series, you can actually get a movie. This is from Marius Spence group, published last year. And the colors here correspond to the colors on the reaction coordinate here. Again, you're going to have to look at this in the middle of the evening. We don't have time to discuss it, but by varying the time between when you excite a molecule in a nanocrystal and when you take a snapshot, you can get different frames of moving. But for each frame, we need many orientations, many views. And so we have to collect data for a long time with each particular delay, so that the nanocrystal keeps tumbling across the beam in random rotation. Let us build up enough projections for one three-dimensional charge density map at one delay between when the molecule is inside the crystal and when we take a snapshot. And this is found to follow this reaction according to the path here, but there are two paths, so they have to be separated out by clever data analysis, single value composition. What you're actually seeing here is the total density of these stable ingredient states accumulated decay during the photocycle. So that's an interesting, if you're interested in time resolver, that's the paper to look at. Okay, here's experimental geometry. The major sources of error. When we started, all the crystallographers in the old hand said this is a stupid idea, it'll never work. And XFEL is the worst imaginable source for crystallography. Why did they say that? They said that in 2003, and there was very little funded research as a result, because every pulse in the X-ray beam is a different strength. You don't have this beautiful, stable condition. Second, every crystal is a different size. So there's a horrendous scattering problem. And they're mapping it up. The amount of scattering goes in proportion to the refracting volume. And thirdly, every crystal coming in is at a different random rotation. So it's asking a lot of the software to account for those effects, to normalize the scaling and the rotation variation and the shot variation with the intensity. That's really the heart of what we're going to learn about today, how to deal with those problems. They have been dealt with, and the best results now are up to about 2-angstrom resolution. And you should bear in mind that there are papers which carefully compare XFEL, the laser results, on the same crystal as have been analyzed for similar material, say, at a synchrotron. So the papers famously detailed shrinking with science last year comparing XFEL. Now, there are 4 cases of correction. I think I'll have to skip this up. You should know that the two most important are the mosaic crystal and the very small crystal. You can read this later. We have the perfect crystal, wafer of silicon. The crystal does act as a monochromator. It picks out one wavelength from the incident distribution. The other wavelengths don't go anywhere. They're stopped by the crystal. The more realistic case, and that this is the case, the asterisk here means that this workshop deals with this case, where you have little children blocks. And then there's bound to be a block in the right orientation to resonate with each component that is refracted for every component wavelength in the incident distribution, because the energy coming in the XFEL still covers a range of energy, a range of wavelengths. And the tilting of the blocks picks out that different wavelengths. And so every wavelength goes somewhere. Every wavelength goes somewhere. This one sample monochromates. Only one, lots of wavelengths go in, only one comes out. Here, if they're tilted blocks, if they extract every wavelength goes somewhere. Third case is nanocrystals. That's a specialized business with a very small index fringes between the spots. And the final case is where the in diameter is smaller than one of that block. And that is analyzed by paper. So here are these fringes running between spots. You don't need to worry about them this time. I would remind you that the gray dental Hawking code have actually seen mosaic blocks. This is in Lysozyme, I believe it's the first time it's been done. They did that by Cryo-em. So obviously the thing to do is to use these Cryo-em real space images, no phase problems, real pictures like a camera takes, of proteins in a crystal to construct your model of mosaicity. That's the sort of research topic we're working on. If, as I said before, you just add the same rag spot to different crystals, then it's a plus-on error process, and the error in your measurement of the structure factor falls off as 1 on the square root of the number of shots. This is data from my Carol Nass on detection. And you see that if you've got enough data, you can get that. That's the calculation you want. Although it's a law of diminishing returns, in which you need 100 times more data to add one significant figure. This is a terribly punishing and severe penalty for working across our statistics. 100 times more data needed to add one significant bigger your results. But that applies to the software you're learning about today. I'll skip over partiality, but I want you to have these PowerPoints because they refer to the important papers. This is an analysis by Berkeley Group showing how partial reflections are made up. This shows you what's happening in the partial reflection. This shows you, I'm nearly done, that the time, because of improvements in software and in instrumentation, the amount of data you need to solve the structure has gone down dramatically in the last 5 years. We used to need millions of shots collecting data for several days. Now people have done it with 1,000 shots. But do remember, you can't apply to the LCLS or the SACL to solve a structure. You know, that's considered old hat. I mean, the software is really sophisticated, and that would not be sufficiently novel scientific direction to get you beam time, unless there was a radiation, there was some angle, you know, there's some aspect of the problem about radiation damage that required the use of an X-ray laser. You must require unique instrumentation in your beam time. Okay, here's the second last PowerPoint. This is the database. Now, this is, I'm sorry, this is out of date. In 2013, there were 15 data sets. This is the direct web address. Nobody's changed the web address. That's where you need to look. Here are some important data sets, favorite, others, others. And finally, I want to tell you that we're here to help you. This is a consortium of 7 American campuses, which has been set up by the NSF. It will run for probably 10 years. It has about 6 or 7 biologists. They're in blue on the left, and about more than 7 people in red who are methods developers, people like myself and I. And our job is to help anybody who wants to use the LCLS or SACL for structural biology. But please send me an email if you want to write a beam time proposal, because I can help your beam time proposals get funded, get authorized. Yeah. We've been through it many times in 6 years. We started in 2009, and it's when the LCLS opened. And the main thing is you have a unique angle that not used for a single time. And we can help with that. So send Nadia or me an email if you want to do some of this work, if you have a problem which requires the LCLS, as I showed in my second PowerPoint. And the other thing is we can give you practical help. We can give you a gadget with 2-bay 5-star, built. We can either lend or sell you a very modest cost. A vacuum box, which goes in your lab microscope with these nozzles in it that the LCP has to test your samples before you go to the LCP. Because in the early days, lots of people showed up and their samples clogged up with jets. And then that's a waste of the day. You only had 2 days of time. So it's really important to make sure that your nanocrystal samples will run well before you go. And that's why you need to be able to look at them under the microscope while they're jetting from these fine nozzles in vacuum. So you need to provide your own vacuum pump. We'll give you the box we've got to the window of the microscope. And we have a full-time professional to make nozzles. And she will make them for you at nominal or 0 cost. Okay, any questions?